Hello everyone, welcome back to another episode of Masters of Code, a video series dedicated to technologists and everything around technology. Today I have James Reinders with me. He's one API engineering evangelist for Intel. A brief introduction about James. He is an engineer at Intel with extensive parallel computing experience focused on enabling parallel programming in a heterogeneous world. James is currently focused on the DPC++ project and the One API initiative, about which we'll be discussing along with SYCL quite a lot. He is an author, co-author and editor of 10 technical books related to parallel programming. And his latest book is about SYCL, again, a topic which we will be discussing in this session a lot. He has had a great fortune to help make key contributions to two of the world's fastest computers, and number one on the top 500 list as well, and many other supercomputers and software developer tools. James, thanks for joining in, and very happy to have you.
My pleasure to be here.
Sure. So we'll directly just, like I mentioned, that this conversation will include a lot of discussion around SYCL and around One API and your role and what you have been focusing on. So let's just jump right in. My first question is, would you tell us what challenge are you currently focused on? What are you working on?
Yeah, it's an excellent question. What makes me excited these days? What's exciting to me is computer architecture is changing yet again. We're seeing an explosion in the different types of accelerators, the specialization of hardware. This is a challenge for us as software developers because we want to take advantage of these items, but it'll be useful to us if we find a common way to do it. Instead of an accelerator from company X and using software particular to that, and then a different accelerator from company Y, can we program in a way that takes advantage of this explosion in capabilities in our hardware to accelerate our workloads and do specialty items for us?
All right. Thanks for sharing that, James. My next question is about something which I know that you really want to talk about, and you have been talking about it in and out, and your last book was also around that, SYCL. So what is SYCL and what does SYCL code look like?
Yeah, so SYCL is a part of the answer to the equation. How do we program all these different accelerators? So SYCL is a set of template libraries. You can think of them as extending C++, but extending standard C++ in the way it was intended to be, with class definitions and template libraries, specifically to do two things. One, to find what accelerators are on your system. Maybe it's a GPU or an integrated GPU or a capability in your CPU or an FPGA or a DSP of some sort, to find them and then to give work to them. And of course, giving work to them means sharing memory in some way, either copying memory back and forth or having shared memory. SYCL addresses all of those issues, and it does it in an open, multi-vendor, multi-architecture way by creating the standard. It's a standard from Kronos, so that I can program in C++ and find and use devices regardless of what vendor or what type of architecture they are.
And what does the SYCL code look like?
It's C++ code. So for instance, you create a queue, which is a connection to a device, and you do that by constructing a queue. You say queue, which is the name of the construct, and give it a name, and it'll find an accelerator and establish a queue. And then you have some things like parallel fors that you can do a queue.parallel_for to submit work to the queue. So it looks very C++ like. It's very easy to learn, and there's a lot of tutorials online, and of course our latest book is available as a free PDF download. So if you Google data parallel C++ SYCL, my last name, you'll find a book that you can download and take a look.
Sure. James, but it's perfectly fine what you said. It makes sense. The question is, why now? Why does it need attention now?
I mentioned before there's an explosion of hardware. So two of the foremost computer architects in the world, Hennessy and Patterson, have described this as a new golden age of computer architecture. So a new golden age for computer architecture, computer architects, to come up with amazing ideas, whether it be an ASIC or standard silicon, or GPUs, or new features in CPUs. There's an explosion, and this has been caused by a variety of technologies coming together. Obviously, clock rates stopped going up. We had this march of more and more megahertz and gigahertz for a long time, but more than a decade ago, that march stopped for a variety of reasons. And instead, we've seen parallelism of many types happen. And if you look at what is happening to our devices now, they're actually a connection of chiplets. If you open up a package now for a CPU or a GPU, it's not one piece of silicon anymore. It's quite often multiple pieces. And some of them have already crossed the barrier of, having more than 100 chiplets together. And recently, Intel and a few other companies announced a standardization, a consortium to define interconnects between these chiplets, so that you could potentially have multiple vendors supplying chiplets that are connected together. There are already devices like that in the market, where chiplets come from different fabs, from different vendors. But this is like a computer architect dream, because now you don't have to design an entire device. You could design a chiplet that then connects to something else. So maybe a chiplet that does some acceleration and hooks to a CPU, a standard CPU. We're going to see more and more and more of that. We're already seeing a little of it, but that's why we need to pay attention to this now. We need to be discussing, how do we software developers take advantage of this, because we're just at the very beginning. It's kind of one of those cases where you've hardly seen anything yet, and it's going to get even more exciting at all the different capabilities that are available to us in the hardware, if we can take advantage of them in the software.
Are you hinting towards one API? And if yes, then how is one API and SYCL related? I mean, if I have to answer that, I'll say that, you are a common connect, because I know that you have been extensively focusing on both. But yeah, so how are they related?
Yeah, SYCL, as I mentioned before, is very C++ focused, and it's focused on the question of, if I'm writing a C++ application, how can I find what acceleration capabilities there are? It might, it might be in a GPU in my system, it might be in a chiplet, who knows where it is. How do I find it and use it from C++? But the world's much bigger than just writing code in C++. So one API broadens that and says, well, okay, how do I do the same thing, but maybe in Python or Fortran, or in a library, a math library or an AI library? It's really a philosophy. It's a philosophy that I should learn how to do programming in a way that then can take advantage of whatever architecture, whatever vendor accelerator is available to me. So instead of, if I'm programming an FFT or a DNN, I should be writing it in a way that then can take advantage of whatever hardware I happen to have on the system I run on. I shouldn't really have to learn a different way of programming each device. Because there's going to be this explosion, or there already is an explosion. It's not just one device or 2 or 10. There's literally going to be hundreds and hundreds of different devices that our programs might be able to take advantage of. And so the one API name really comes back to, if I'm going to learn a library, I'd like to learn one library. Or if I'm going to learn how to program in C++, I'd like one method. Or if I'm going to debug my program, I'd like one debugger. And I'd like it to be the job of those debuggers, libraries, languages to automatically know about all the different accelerators that might be available in the system and give me access to them. Now, there may be some work for me to do. It's not all automated, but I'd like to have a common capability to take advantage of accelerators rather than having to learn a whole different software stack for every accelerator. That would be unsustainable.
Sure, makes sense. For someone who's interested, let's say, to work on this, to learn more, what advice would you give, and how can somebody try it out?
Yeah, so I think I'll turn that around to, it depends on what you're interested in. So the best advice I can give you is think about some problem that you'd like to solve, or some part of your application, and then look for the part of one API that's trying to take this philosophy and make it alive. So if you're a C++ programmer, by all means, go learn SYCL. If you are interested in BLAS or math libraries, take a look at what the 1MKL specification does for us there. It ties into SYCL, but it dispatches to devices in general. Or look at 1DNN and what it makes capable for DNN programming, or look at the Python support in one API. No matter where you start, you're going to find a philosophy that we're trying to give a way to code or use a library, use your tools, your language in a way that's agnostic to the hardware, the architecture. And I say agnostic, meaning that the tool itself will survive across all these devices. There's still maybe some work for you to do to set up your code so it's able to take advantage of all of these, but you do it in a manner that's flexible and scales with whatever machine you're on. So go take a look, and you can start off at oneapi.io, or you can start off with the SYCL book if you're a C++ programmer, and then go look for the part of one API that's trying to help the type of programming you do, and get on board with the philosophy and join the discussion and help us, because this is an evolving capability. There's some parts that are very strong, there's some parts that are emerging, but it's really a philosophy that we need to write our software in an open, multi-vendor, multi-architecture manner.
Sure. James, I want to take a step back and hear you. My question was also around that people who are interested, right? For them, what's the way forward? How can they go about learning, which you answered. I want to take a step back and understand that, in your opinion, for whom does it make a lot of sense to try out one API or SYCL? Are these your typical hardware engineers only, or people who are software engineers, or who are kind of transitioning in between, who are working across platform? For whom does it make a lot of sense, mid-level, senior level?
So I think one API, let me answer it a few different ways. One API is should appeal a lot to anyone that's thinking about the architecture of their software, because one API is helping answer the question of how should I architect my software to take advantage of lots of different hardware. So for instance, you could write your program, you could architect it and say, okay, I'm going to write it in this language, and I'm also going to use some CUDA code. And what you're doing when you do that is you're saying, gee, I want to be able to take advantage of an NVIDIA GPU. Of course, you could go and find an SDK for some other piece of hardware, and you could use it. But each time, traditionally, you're being asked to make a decision to use a particular vendor. So the question is, can you step back and architect your program so that it can use multiple vendors? So if you use SYCL, you can produce code for FPGAs, like an Intel FPGA, or an NVIDIA GPU, or an AMD GPU, or an Intel GPU. You can write your code in a way that can take advantage of all of those. You're not architecting it to be dependent on one particular vendor's software stack. Now, this is emerging. The thing I just mentioned works quite well. And when you look at some parts of it, some parts are more emerging than others, but there's very solid support there. So it should appeal to architects. And then it should appeal to the implementers that implement that architecture in terms of getting in there and writing the code so that it's more portable and performance portable, meaning that your application can run on different hardware more easily, and that it generally gets good performance wherever you run it. Generally, you may have a little work to do, but it's more performance portable, meaning that you haven't tightly coded it to one particular piece of hardware unnecessarily. You've made your code more flexible.
That makes a lot of sense. Thanks for sharing that, James. Just a couple of more questions. With respect to one API and SYCL, what does future look like? And in future, how you see them evolving?
Yeah, well, it's an idea that is appealing to a lot of people, as you would expect. That as we see more and more novel hardware become available, it makes the problem more important to solve. And so with that, what we're seeing is in the open source community, more and more people participating. So the effort to implement SYCL, there have been multiple SYCL compilers. I think there's 5 or 6 of them now. But one of the really important projects is called Data Parallel C++, and it's an effort to add SYCL to the LLVM compiler. And the LLVM compiler, Clang, their C++ compiler, there's a project to add SYCL. Well, that started as an effort by Intel to support Intel devices, but now it's been extended in the open source community for NVIDIA and AMD GPUs as well. And that's really exciting because it's one compiler now that supports multiple. We've also seen like the 1DNN library, again, initially started by Intel to support Intel devices. It's been ported to take advantage of acceleration on ARM devices, and it's been used extensively on the world's fastest supercomputer, which is ARM-based, and in Japan. So we're seeing more and more people say, wow, this is a good idea. How can we help? And getting involved in the open source community, contributing to the specification, contributing to software that implements one API, implements more vendor support. So we're really at that exciting stage where things are gaining momentum. And I think what the future holds is there'll be more and more discussions. How do we extend this? How do we take advantage of low latency fabrics? How do we, so that we can distribute our problem across more devices, maybe multiple different types of accelerators doing different parts of the problem. There's a lot of exciting topics in our future that are really energized by this open community support and discussion. So I see more and more momentum behind it, more and more participation. And I expect over the next few years, we're really going to see an explosion in the support and activity around one API and one API-like activity to get this open multi-vendor, multi-architecture support that's so critical to programming heterogeneous machines.
All right. I think if I have to summarize, I'll say that what you mentioned from more and more participation, momentum, and of course leading to an explosion, which is going to happen. So yeah, I think that's very detailed, and thanks so much for sharing that, James. Just the last question, very generic one. Your final thoughts or words of advice to our listeners, these audience developers across the entire world.
Well, I think getting used to the idea of heterogeneous programming is important for all software developers. So I would say jump in, try it out. There's no better advice I can give a software developer than go find some way hands-on. So if you do a little Googling and look for one API tutorials or SYCL tutorials or one API Python, there's something there that should intrigue you. Go learn it, go play with it, go take advantage of it. Intel has something called DevCloud, which is a free access online. So if you don't have the particular hardware to try out that may have the latest and greatest CPUs or GPUs or FPGAs, you can get access to that online. So there's no excuse to not just jump in and try it. So don't just read things and watch videos about it. Go actually find some code, write it, try it out. You'll find that gets into your head this opportunity to use accelerators and use multiple of them and be versatile in your coding, that really happens when you write some code and try it out. So go do that. That would be my best advice for any software developer.
So I'll also kind of add +1 to that. People should go out and try that. And I think that should be it from my side, James. Thanks so much for your time. And I must say that that was a very resourceful and very compact session. And I would urge people to kind of probably go through it twice to understand the intensity of words which have been thrown. Thanks so much again, James, for your time. It was lovely hosting you.
It was a pleasure talking with you. Thanks.